So today we're going to be talking about loops and vectors, basically. To add on to what we were talking about last week, where we were learning about functions, now we're learning about more things we can do in functions, including how to repeat ourselves multiple times over a list of objects. And we're going to go a little bit deeper into vectors themselves. I keep alluding to them throughout the semester. We've used vectors, we've used lists, but now we're going to learn a little bit more how to use them in base R, because oftentimes when you're working with loops, for instance, which we'll learn about, you want to be using a vector. So I will get started and share my screen. Okay, we've got our little R markdown. Let me zoom in once more here. We've got our R markdown, and the first thing we're going to talk about are vectors. So R basically has 6 types. Well, it has 2 types of vectors, and then it's got 6 types of vectors. That's very confusing, but let me explain. So R has 2 types of vectors. So we have atomic vectors and we have lists. So an atomic vector is a vector, like we've been working with, where everything has to be the same type. Everything has to be the same type. Lists, however, can have a lot more flexibility. So you can have lists where within the list, you can have different types of data. So you can have character and numeric, and also lists within your lists. So we can say are flexible to contain many data types. So if you've ever worked with things like a JSON file, in a JSON file, you often have data in a nested structure where you've got data in one cell that's one value technically in the cell, but you've got a lot of values in between. And that can get pretty complicated, but you can have lists like that, and we're going to explore what those look like and how to create them. So within atomic vectors, there's then 6 data types. I'll write them down here, but these apply to lists. They're just different data types as well. So we've got 6 data types, and we've seen these, but it's useful to go over them in detail. So the first one is logical, which is true, false. We've used this a lot. We also have integer, which is complete numbers like 1, 2, 5, 7. They have to be complete numbers. And in R, they're written 1L, 5L, 7L, which just means it's a whole number. I don't know what the L exactly stands for there, though. Then we have double, which is our normal numeric type, where it could be like 4.35, something. Negative 51.6, anything that is numeric, pi, for instance. Then we've got complex, which very rarely will anybody use this, so I'm not going to go into it. And then we also have raw, which is byte level data. And those are, how many is that? 1, 2, 3, 4, 5. Okay, that's 5. And then we have 2 special cases, which are factor and date. So we've seen all of these in class except complex and byte. The factor is a special case of integer, because technically they're integers. It's 1, 2, 3, 4, 5 with labels. So it's a labeled version of integers. And then date is a special case of double, where it's got some additional information wrapped into it. So these are the 6 data types in R. We've seen most of them. Now, how do we actually work with them? So I'm going to start building some vectors. Remember, we put a C at the beginning of our vectors to basically see what these vectors do and how to see what type they are. This seems like it could be something done on day 1 of the coding class, But if we did this day one, everyone would be incredibly bored and not really grasp what we were doing. So now this should be all very straightforward and understandable to us all, but it should supply us with some understanding of what's going on. So let me do a double first, because that's one we've worked with a lot. And I could do C, and then there's many ways I can declare a numeric vector. I could do 1, 10, 2, something like that. And then afterwards, I can see what double looks like. 10, 1, 10, 2. I can ask, what is the length? And length in this case, as you saw last week, is how many spaces are there being taken up, basically. So if we look at length of double, we can see there's 3, because there's 1, 2, 3 numbers total. 3 items in this vector. We can also say type of. So you've often seen us use class. If I say class of double, it's just going to say numeric. But if I say type of double, it will actually say this is a double type. Class is more higher level, while type of is more specific. So it will explicitly say what type this is. And, you know, we can use evaluation, like is double, and true, it is a double. We can do this with every single type of vector we have. We can do it with an integer, which would, as I said, we declare it with an L after every number. So 1L, 10L, 2L. We can do all of these same questions. So we can say length of int, type of int, and is, let's try is double on it. And it should say no, it isn't, because it is integer. And yeah, now it says true. So it's not a double, it's an integer. Those are different data types inherently. We can do the same thing on character. Now I'm really confused why character isn't in this list. It must be absorbed into complex or raw, because that is a type that we use a lot. But, you know, we've used character vectors where we could say like, hi, hello, good morning. And then the same exact steps. Length is going to be 3, type of this time. We say type of char. It's going to be character. All the same steps for all of these, whether we do a true false one, where we could say logical is true, false, false. That's going to then declare as logical. So I think this is pretty clear. I think, you know, we've got a few things we can use to test these types of vectors, and a vector is declared with a C in front of it, which means combine. Now, all of these vectors, I can make named vectors. So if I want to declare a new vector, I can say horse is 7, man is 3, dog is 8. And now when I call up my vector, you can now see each of these numbers in the vector. We still have only 3 numbers total. We still have only 3 items. They now have names though. And to subset this vector, and this is a word you'll see a lot, vectors subsetting, we use brackets after the object. So the object is X. We can see that up here. We've got a value called X. And to subset different parts of this object, I use X and brackets. So inherently, a vector only has 1 dimension. So if you're working with data frames using this base subsetting, you would have to use a comma in between for rows versus columns. We don't need to do that right now. We're just using the brackets, and we can say which number out of this list that we want. We can say 1, and that should bring us only the first item. We can say, let me make this multiple of these. I can say -1, which will give us everything except the first item. I could say 2 through 4. We don't have a fourth item in the list though, so let's see what will happen here. It gives us 2, 3, and then an NA because there isn't a fourth item. And this works with any type of vector, whether it's character, logical. This is how we limit the items that we want here. We can also extract these based on the name of the index. So if I want, let's say, just the one that's named man, I can say here, man. So by saying man, I'm calling on the second item, and I should get man 3. And I do. If I want to do more than one of those, I have to do a vector inside of a vector. So I would have to say XC, comma, and then let's do horse just to mix up the ordering and show you that it works. So it would be the second place and the first place, just those two. I then get man and horse because I've called the names of those indexes in the list. One more thing we'll look at really quickly is using double brackets. And double brackets come more into handy in lists, but I want to show you what that does in our case here. So if let's do X1. If I do X1, we see horse 7. If I do X1, it's then just 7. And that's because basically this extracts it twice. So it first extracts it. Oh, I've got a chat. How do I mean return index for man? So in this case, in X, we've got 3 different indexes. We've got index 1, index 2, index 3, and the second index is named man. So I can either say this is the second place, but it's also called man. It has a name. So if I supply the name of the position, it will come here. Now, if I add a fourth one with the same name, I believe this will work. So let me try it. Let's do man equals 2, no, 4. Now, if I do X man, it should come up with both of them. No. Okay, so that doesn't work. Ignore that. Have unique named vectors. I'm surprised it didn't give me an error in that case. But hopefully that cleared that up.
My question actually is, how do you just return 2 for the man?
Oh, just return the number.
Yeah, just 2 instead.
That's a good one. I think it might be which. Let me try this. Which X man. This is me just experimenting. No. There is a way to get the index. It's just something that I do so rarely. Let's see. Okay, I'm not seeing that one right off the bat of how to do that, but I'm sure it's possible. I'm just not positive. It's more like you would use an index inside of an index. Generally, if you wanted to know what space it was in, like if it was the second one, you would generally use, this is going to sound really confusing, but you would generally use something that would evaluate as a true or false to then apply that to another vector so that the true or false comes in the right order. I actually have an example of that in a few minutes. I'll show you that, and hopefully that helps. And then to answer Sydney's question, perfect. So when I did X1, I just got horse 7. When I do X1 of X1, basically, this says, let's see X1, which was horse 7, and then let's extract that element. So it's, in this case, it's getting rid of the name. This is more useful in lists, and I'll show you a little bit more of that. But if I say unname, I believe that's how you spell it, unname X1, it will give us a very similar thing in our case. But if you have nested lists, you actually have to use this when you're trying to extract like sub elements. And we'll see that in a minute. Okay, now we're going to work with lists a little bit. That's a perfect transition. To make a list, we've seen this before. We use the command list instead of C. So let me make a heading that's called lists. And then now I can say my first list. And then I'm going to make a list where the inside of the list, I'm going to have an element named X, which is going to be the value of A. Then I'm going to have an element Y, which is going to be the value 1. Then I'm going to have Z, which is going to be a vector of integers. So I'll say 1, 2, 3. And then finally, I'm going to have an unnamed element. So before we had X, Y, Z were all the names. This one's not going to have a name, and it's going to be a list of A and 1. So you can see, because it's a list, we can mix data types. And now let me just run this and show you what this would look like, because it's kind of confusing when you're reading it. So let's walk through this. Let me give myself space. And if you want to copy that one, since it's got some technicalities, I'll paste that in the chat. So in my list, the first thing is X. The name is X, the value is A. The second thing, the name is Y, the value is 1. The third thing, the name is Z, and it has 3 values because this one's a vector, 1, 2, 3. And then the fourth item, you'll see we start getting these weird double brackets here. Try not to get confused. It can be off-putting in the beginning, but the fourth item doesn't have a name, so it's called 4. And both of these are called 4. But 4-1 is A and 4-2 is 1. This is a list. Now, if we type length of my first list, we can see that it has 4. Even though we have more than 4 items here, it's what is the length of the highest level? So we've got A1 vector list. That's 4 items, so we're evaluating to a length of 4. And another way we could look at this list is using str, which stands for structure. We've used it before. It doesn't stand for string, even though every time I read it, I think it stands for string. So we can say my first list. And here we can also see it a little bit better. We've got X, we've got Y, we've got Z, and we've got no name, which is a list. So we've got a character, a number, an integer, and then a list of 2, and it gives us the sub items in the list. Working with lists is similar to working with vectors. We're going to use a lot of subsetting with brackets. So I can say my first list, and if I subset items 1 through 2, I can now pull out just items 1 and 2, which was A and 1. I can also subset with the names of the locations like we did in the vector. So I can say my first list Y. And this will pull out the second item because the second item was named Y and give us that. This also works with my first list Z, where it'll then give me the vector 1, 2, 3 because the vector is named Z. Now let me try the same two, extracting Y and Z by using those double brackets. So if I extract Y, enclosing that in double brackets, now instead of saying Y is 1, so keeping it in that kind of hierarchical list, I guess you could call it, where we've got a list, we've got the names, and then we've got the values. When I do the double brackets, I just get 1. I get that interior of the name. I don't even see the name anymore. Let's try that with Z now, which was a vector instead. With Z, you can now see that just evaluates to a vector. If I say class of my first list, it'll probably say numeric. Yeah, it's not going to give me anything that says that this is a list because these double brackets take it out of the list and just make it a normal vector without any names. This is something that takes a while to grasp. Oftentimes, if you're struggling, you just end up using both and see which one works for you, and that's okay. That's how we learn. We can also, just like in data frames, use the name of the location, so Y or Z, to extract it with the $sign. So I can say my first list $Y. Now, we didn't use the syntax for most of the class because this is base R, but we did see it last week, and we can extract now anything Y, Z. The only one we cannot extract is this fourth item because it doesn't have a name. So we should probably give it a name. How do I give a name to the fourth item in the list? What I can do is, anytime I'm ever wanting to work with names, I can use the names function. I can ask for the names of my first list, and we see it's X, Y, Z, empty. So let me show you how we would rename this, and hopefully I'm going to kind of go through it a little bit fast and explain it after instead. So I'm going to say names of my first list, and I want the fourth one. So I take the fourth item, because this is a vector technically, and I want to assign that a new name, and I will call it A because X, Y, Z, A. Let's flip it around to the top of the alphabet. And now this will name my first list. It's going to change this, even though it's got like a function and it kind of looks backwards to how we would normally see it. This is going to evaluate now for if I ask names of my first list, this is now called A. And so now I will be able to say my first list A. And it will give us this sublist. So the elements of this are, I need to call specifically on the names of this list. I want the fourth one, so I have to say which location I want, and A. I could have also renamed all of them at once without saying which one. I would have to give it a vector though. Now I'm trying to find the one that I told Ash I was going to show you all with the true and false, but I think I took it out of the lesson. Oh no, I didn't. Okay. This will be jumping back to vectors though, but it's the same as lists. That's okay. So now if I have a, let's say working with logics. So let's say I have a vector X. I'm just going to overwrite my other one where it's got I like dogs. And then I've got another vector called LVec, for logical vector, and it's the same length. And I have true, false, true. I can now use LVec to subset X. So if I say X LVec, this is going to say true, false, true for each of the locations in my X vector. So the first, not the second, but the third. So it should say I dogs. And that is what happens. So this is how you can start previewing complicated uses of vectors because you're able to say something like, let's say X, and then say I want the number of characters to be more than 2. I could say nchar of X more than 2. That should work. Yep. So you're able to use things that will evaluate to true and false. Like if I just run this in the command line, you'll see it's false, true, true. This will evaluate my vector, tell me which locations in the vector that I want to manipulate, and then it will apply it to the vector and give me the results. So this is how, if you can expand your mind a little bit, the base R data frame manipulation also works. So instead of using filter and select, it's a bunch of complicated brackets with different functions applied to them, and it can get very confusing. But this is just to preview that this prints out a false true true, which then we can apply that false true true to the X vector, so it prints out our result. Okay. Any more questions on vectors or lists? Doesn't look like it. Okay. So now we're going to go into loops. So this all was like, could have been taught in class 1, but we waited because it's not very fun and it's a lot of detail. You just kind of learn as you go. Now what we're going to learn are loops, which is something that most of you have never encountered before. So as with functions, we talked about how we didn't want to duplicate our code too many times. We didn't want to copy and paste. We didn't want to do that duplication. And that's because if you create a function, or you'll see if you create loops within your function or outside, that it's easier to see the intent of your code so that people are able to read it clearer. It's easier to, if you have changes in requirements, what you need to accomplish with your code, you're able to edit it easier and you don't have to remember like, oh, the same code is up here, the same code is down here. And then finally, you're able to find bugs easier because it's in less places. So that's why we used functions. And that's also why we're going to use loops. So loops are a form of iteration. If I want to do something many times, instead of doing a function where I could say one of the functions we built last time, I could call it on function 1, function 2, and do the same thing over and over for a bunch of different numbers for the function that I created. We can do loops where we call it once and it will do the function as many times as we wanted it to be done. Let me show you what I mean by that. And so the basic loop syntax, I'm going to write this in a chunk and then just tell it not to evaluate, is for variable in vector, do something. And this is eval equals false because this is not working code. So this looks kind of like the function syntax we wrote last week, where we've got our curly brackets, where we do something inside of them based on a variable that we declare. But this variable in vector, that's the part that's new. So let's see what that could look like with a minimal working example. So I can say for I in 1 through 10, and then I'm going to explain this, don't worry, print I. So when you're working with loops, oftentimes we call them I or we call them J. We name it something, the value that we're going to be looping over. Sometimes you want to be very explicit and say what exactly it is you're looping over. In this case, I'll just say I. So I represents the number in the loop. And then 1 through 10 is the vector that we'll be looping over. Let me print this out and so I can explain it better. So for I in 1 through 10, print I. When I run this, what's internally happening, these are 10 different commands that were run, is we're going through each number in the vector. We're going for the first number in the vector, then the loop finishes, then we're going to go through the second number in the vector, the loop finishes, the third number, etc., until we reach 10. So because this is very simple, all it had to do was print out the number. We had 1, 2 through 10 because we had these 10 different values that needed to be printed. And that, again, is because of the vector we're supplying here. If we do 1 through 10 like this, remember that's a vector of 1 through 10. So we don't have to loop around a vector. We can also loop around characters or lists or any other sorts of vectors. So I could do the same exact thing, but instead of supplying 1 through 10, and because it's so similar, I'm going to copy and paste it. Instead of doing 1 through 10, I'm going to create a vector where I supply it different words. So cat, dog. Now it will go through each value of this list, each index, we could say, and print out each individual one. So we print out cat, then we print out dog, then we print out gerbil. So these are 3 different tasks that are being completed. finally, we can do the same thing with a vector we've already created. So let's call on X, which was I like dogs. If we call on this, it's going to print out, it's going to go through each index of this vector and print out each index. That's all we're doing in this loop. So that's great. Loops are made for much more complicated things other than just printing out all of these vectors. So let's get into some more complicated things. First, let's say I want to exponentiate, no, that's not the right word. I want to put all of the values in my list to the power of 2 to an exponent, or in my vector. Now, in R, we have things like sum, which are a function, but if we want to put something to an exponent, it has to be like x to the power of 2, or also x2, which that's the two different ways you can make something into an exponent. Because this is more of a mathematical operator rather than a function, it's harder to grasp how you would apply that to a list. Like, okay, we've got a list called double. If I wanted to multiply, no. If I wanted to take the mean of the whole list, I could say mean of double, that's clear. If I wanted to make all of those numbers in the list, though, squared, I guess I could say x to the 2. But you'll see x to the 2, non-numeric argument to binary operator. Well, that's probably because x is not numeric. What about double? So double squared does work, where I take each value in the list and I can square it. But again, working across vectors, doing these vectorized functions, some people have a hard time grasping that. So let's do this instead in a loop, where we're going to take each value of the vector and create a new list or a new vector that has the index squared. So let's see. We are going to draw a loop first. And then before I run the loop, I'm going to explain why I want to do some other things first. So for my loop, I'm going to say for I in 1 through n. And this is because I want to declare what my n is and be able to change that. So what's the number that I want to work with? Start my my curly brackets to start my loop. And now I know I want to do I squared, but this time I want to actually assign I squared to an object. So I'm going to create a new object. Let's call it banana for fun. And this time I want to take the index that I'm working with and apply I squared to the same index of banana. So here I will be saying for, let's say I is 1. For the first item in banana, take 1 squared. Now before I run this, I want to declare my n. So in this case, I want n of 5. We can change that later. And this is just because I want to be able to change this kind of like a function. I want to be able to change this to different values of n. And then also, before we run this, we often want to allocate our memory first. Now, in R, in computers in general, allocating memory can take time. So if we were to just say, make an empty vector, and then for each value, grow the vector, we'd have to basically have our computer stop for a millisecond, allocate new memory every time we do it, and then create a new vector each time, like make the vector longer. Instead of doing that, it's a lot nicer on our computers, so people tell me, that we declare our vector first. So we always have to declare it because otherwise it doesn't know what banana is. We'll declare our vector, but instead of making it empty or just null, we actually can say vector. So this will be a vector. The mode, so what type do I want it? I want it to be a double. And then I have to declare the length. So how long do I want this vector to be in? So this is so that we allocate all of our memory first before running our loop. So in this case, our length is going to be equal to n. So whatever this is, it will evaluate. So I can just run the whole cell this time. And then, well, let's call banana first. So now I can see that it's 1, 4, 9, 16, 25. So this lets me loop through the numbers of 1 through 5 in this case and square all of them. What if I wanted to loop through the first 100 numbers of our number system? So instead of doing 5, I could do 100. And instead of just looking at them, I could easily take the sum of them. So if you've ever wondered, what's the sum of all 100 first squares? Well, you probably haven't wondered that, but we're going to figure it out. And I could call this square instead, but it's banana now. So now this will take the 100 first numbers of the system, go 1 through 100, square each of them, and then we're just going to take the sum of all of that vector. So that's 338,350. So yes. One thing that we might want to change that I'm going to do from here on out, though, is instead of going 1 through something, we often want to say instead sequence along. And let me show you exactly what that looks like. So I would take this same function and do sequence along instead. So I'm going to sequence along 1 through n. Let's test that in the console to see what that actually does. It just gives us our 1 through 100, but when we say sequence along around it, or we say sequence along double, sequence along int, any of our vectors, sequence along is a little bit more error friendly. So if you have an empty vector, for instance, which sometimes can happen on accident, 1 through an empty vector will often cause us to fail, whereas sequence along has checks built in for that. And so the best practice is to always call it along sequence along. So we could easily do this loop with sequence along, let's say something numeric, int. So we can sequence along int, which will take us through each of the values. And it will now have our new banana. Okay, that rewrote the first 3. That makes sense. Because banana was already allocated. It rewrote the first 3 because int was 1, 10, 2. I think that's what happened. Something like that. I'm sure we're fine. Okay, so now, unless we have questions, I'm going to take an example of how to just pretend we don't have the sum function and how we would basically sum together items in a list, and then how we could get the cumulative total. So I'm also going to connect the loop now to a function as well. So we can like create a function that will give us this output. So let's do a sub heading, and we're going to say total and cumulative total. So, you know, we've got another vector. Our vector is x. It's got the numbers A, 1, 3, 1, 3. Shouldn't name your vectors x, but we are in this class. If I didn't know the sum function existed, I probably would end up doing something like x of 1 plus x of 2 plus x of 3. I'm already making mistakes, which is a great example of why we shouldn't do this. X of 4 plus x of 5 plus x of 6. Okay, there's no 6th value, that's why. There we go. I was like, that has to work. So this takes every element of a vector and adds them together. But you can see even just in me typing them, this is not efficient. We shouldn't do this, because what if we had 1,000 values and we wanted to add them all together? So instead, we could do a loop, which will basically take the first number, add the second one to it, save that, then take that number and add the third one to it, save that, take the fourth number, add it to that list, save it. And so that's what we're going to do first. We're going to build a function called total that has a loop that will add all of these together. First, though, which is best programming practice, I'm going to work on my loop outside of the function to build it and make sure it works, and then I'll build the function. So because I want one output, I want one number, which is the total of all the numbers in the vector, I can just say sum val. So that's the sum of my values is 0. I don't have to declare vector ahead of time because it's 0 is a double. And so when I say 0, it will know that it's double and it will know it has a length of 1. So I don't need to declare it specifically. Now I can do my loop, which is for I in. Now here's the trick. We're going to do sequence along X. So X is here. We want to sequence along X. So we want to go through each one of these. Start my loop. And here I want to take sum val, which currently is 0. Then I want to save sum val plus X of I. I'm doing X with double brackets just to make sure I don't have anything else I'm dealing with. I just have the smallest number possible, least extra information, I guess you could call it. So let's first see if this works. So we've got X. Now let's try this, and let's also, so we can see what's going on, we can always build in print statements so we know. I'm just going to say print I so that I know which number it's going through at the moment, and then sum val. So when I run this, okay, we went 1, 2, 3, 4, 5. Those are the index of the numbers, though. It's not the number itself, that's the index. So it went through all 5 numbers. And then now, let's see what sum val is. Sum val is 16, which makes sense because that's what that adds up to. Now I know this works now. I've tested it. I put a print statement in to make sure it was doing what I wanted it to do. It did. So now I can actually build this into a function. So let me build a function called total, where I can declare a function by saying function of, and here I'm going to call it vec, because I want a vector. I could call it x though, but since we've already got x in here, I don't want to be too confusing. Let's do function of vec, and then we're going to do an open curly bracket and a closing curly bracket. Notice my formatting is already getting a little messed up. Anytime you want R's formatting to be fixed, you can do Control I, and it usually does a base formatting fix for you, which looks pretty nice. So we've got function of vec. Now, instead of x here, I actually am going to want it to go around the vector. So I probably want to say sequence along the vector, take the index of the vector. That should work. And now in this function, I actually want to declare some value. And that's because we want this to be part of the function where we set some value to 0, and then we're going to add on the total. So that looks good. We probably also want to build a stop. So I can say if is numeric vec. So if vector is not numeric, I can say stop vec needs to be numeric. And then I'm probably going to want to build a return because at this point, nothing's printing out to me or nothing's getting saved. So I probably want to say return sum val. So this is combining both our loop, which is right here, and our functions, which we learned last week. So I can save this function now. We've got a function called total. And now I can say I want the total of vector x. 16. Perfect. It returned it to me. I've got the number. It should be the same as saying sum of x, but we built it ourselves, which is pretty cool. I can also get the cumulative sum. So instead of just getting the total, what if I wanted to say the first number, where is it? The first number is 8. But what if I add 1 to 8, then I add 3 to that, then 1 to that? I want to see it incrementally. I could also easily adapt my current function to serve that purpose. So if I want to create a function called let's call total cum, like cumulative total. Let me copy this and adapt it for that purpose. So let's change the name to total cum, or let's say cumulative total. That sounds more, flows off the tongue easier. So here, because I'm going to want a vector that isn't just 1, I'm going to want a vector that is the same length as my current vector. I can say here vector mode equals double length equals, that's the length. And here I can say the length of vec, whatever the length of vec was, make it the same length. Then in my loop, I can still say sequence along vector. And then instead of adding everything to sum val, I actually want, let's call this cum val instead. This is why we don't copy and paste code and edit it as we go, but we have time limits. I want to take cum val, save it to the right index. So the first cum val, take cum val plus vector. Now here's where it gets really tricky, guys. Let's say I'm on the third number. If I'm on the third number, I'm saving the third number. I want this to actually add the number before it, not the third number. So I can't just say all of cum val, because first of all, that's not declared yet. It's only partially declared and we're filling it up as we go. And I can't say cum val I, because that's our third spot, but I actually want to add my vector to the second spot. So here I can say I minus 1. This is saying the previous index location that I'm currently in, add that to my vector number. So my, the third number in the vector, add that to the second number in the cum val, and save that to the third cum val location. If this isn't making sense, you can test it, try it out, see what these different things are doing. But right now I can tell you that one thing is going to break us. And so that is that the first number, this is more of an edge case, like what are these different possibilities that are going to happen in this loop, in this function? And there's an edge case, which is those things of the first number in our vector. Currently, the first number in our vector is 0, but we don't want it to be 0. The first number in a cumulative sum would be equivalent to the number in the other one in the vector that you're working on. So here I'll have to build an if statement. You can see how quickly these get complicated. They're not necessarily complicated, but you have to build in different checks. So if I equals 1, so the first index, I actually want you instead to say cum val, the first one, and save that to be the first number in the vector. But instead of saying 1, I can say I, because I is 1. That makes it a little bit more less error prone. But so the first value of the vector, save that to the cumulative value, else do this other thing we've built. I'm just reading through this, making sure I think it'll work. I think it'll work. So let's try it. Let's run this function and then run this on X, which we've been working with. Let's see if we break. Nope. So we've got 8, 9, 12, 13, 16. 16 is still the total, like the other function we did, but we're incrementing by the values of X. So we've got X here, whereas 8 plus 1 is 9, 9 plus 3 is 12, 12 plus 1 is 13. 13 plus 3 is 16. Hope you're all following along here. This also is the same thing as come sum. Is this it? Come sum of x. Same exact thing, but we built it from scratch. Now I'm going to go over one more type of loop now before we move on, and this is called a while loop. It's a double while loop. So if you've noticed in all of our for loops, let's see, like here, we know exactly how long our loop needs to go. We know our loop needs to go to the length of some vector that we declare, whether it's 10 times, 1,000 times, we know how long it needs to go, but sometimes we actually need our loop to continue on until some other condition is being met. So for instance, if I have a simulation where I'm flipping a coin, well, I might want to say, oh, this coin flip happens 4 times in a row where we get the same result for the loop to stop. So instead of saying run it this many times, run it as many times as you need, count how many times, and do this other loop. Very useful in simulations, less useful in data analysis, but you might see this type of loop in statistics classes where you're working with things like probabilities and you need to calculate the probabilities. So I'm just going to show you an example of a while loop so that you can kind of understand how it works, but I'm not going to be asking you to write any yourself. So I'm going to do the example of a coin flip for you all. So the first thing, I need to create a function called flip, where it doesn't have any input. It just takes a random sample where it's 50-50 between tails and heads. And then the probability is, oh, the size is 1. There we go. So here, if I just run this, you'll see in the console, if I keep running it, sometimes it'll be tails, sometimes it'll be heads, and it's a 50-50 split because I didn't declare anything else. So I didn't declare probability. So now, if I call flip, it's going to give me tails or heads depending on probabilities. We're getting a lot of tails suddenly. There we go. Whew. That was getting less and less likely. So we've got a random coin flip. Now here, I'm just going to say flips equals 0 and n heads equals 0. And this is just setting up a counter for how many flips I've done so far, and then setting up a counter for how many heads in a row we have. And our while loop, we want to say, I want 3 heads in a row. So keep running this loop until I get 3 heads in a row. And how long is that going to take? How many coin flips total? So I'm going to say while n heads is less than 3. And then if, let's run a flip. And if that flip is heads, we're going to do one action, which is take n heads and add a 1 to it. So take the number of heads we have, which is 0, add a 1 to it. So then we'll have 1 number of heads. Else n heads equals 0. So let's say we've had 2 heads in a row, but then we get a tail. We want to reset that n heads to 0 because we lost our streak. We had 2, we got a tails, we have to reset that back to 0. And then after this if statement is done, so after we've done a flip, we're going to want to add to the counter. So we can say flips is flips plus 1. So we just want to increase the counter by 1. This will happen every loop. It'll keep flipping, keep flipping, keep flipping until we get 3 heads in a row. And now we can just call flips to see the number of heads. So I could build all of this into a function, but for now I'm just going to run the whole cell as if this whole cell was one function. Let's run it. And it took, oh, that's pretty rare. It took only 5 flips for us to get 3 heads in a row. Let's run it again. 20 flips, 31 flips, 10 flips. And then we could run this function over and over, calculate the average number of flips that we need. And that actually goes to, what function is it? It's one of the basic probability functions. I have the symbol in my head, but I don't remember which function it is. I think it might be Poisson. I don't remember. Maybe gamma distribution, one of those. That's why I'm not teaching that class. So you can use things like this to start testing distributions, for instance. So this is a while loop. It's a while loop because we don't know how many loops we need to do. We have more of a condition of how many we need to do until the condition is met. Hopefully that makes sense to everyone. And I will upload this, but I can also paste this in the chat if you're wanting to run it yourself. All right. The final part of our class today is talking about per, which you can see here. We've got per. Per is it's a tidyverse function. It's a tidyverse package that gets us out of using loops. So we've talked all about loops today, and yet we have something that gets us, instead of using loops, we can use per. One reason we talked so much about loops today is because I think it's important for you to understand how they work. You might not only be using R when you're working with Python, for instance. You have to use loops. There's no way of getting around it, I think. You need to use loops to do these iterative properties. R has forms that instead of doing loops, you can do things that are vectorized, but you need to understand how loops work. I think it's basic programming practice to understand what they're doing, and you might end up getting more into data science, getting more into like algorithmic development. There's a lot of different things that you might need to know how loops work, how using things other than loops might save you time. That's all very important. So that's why we talked a lot about loops today, and because loops are kind of fun. They're kind of a cool puzzle to work with. However, per can get you out of doing some of the things that we've talked about. It can get you to, instead of doing a loop, you can use something called map. Instead of doing a nested loop, which is literally a loop within a loop, we didn't cover, but sometimes you have one vector and you have another vector and you want to match all of the values together. So you have a vector of AB and you have a vector of 1, 2, 3. You wanted A1, A2, A3, B1, B2, B3. Like there's other functions that can help you accomplish that instead of writing a nested loop. There's a lot of different functions in per. However, per in the past has been more important than it is today. And one of the reasons why, at least in my opinion, per has partially been replaced is with the thing that we learned in week 6 across. A lot, like every single lesson on per has you do something with, oh, you want to go across all of these columns and apply the same thing to all of these columns in your tibble. Well, we know how to do that. It's in across. We don't need a loop and we don't need per. So I've chosen to keep my per lecture pretty short because it's very specific use cases of where you would need to use it. So I'll go over one way in which you would use per, and then I'll show you another example of where I think per is most useful. And so you know where, at what stage you need to go and learn more about per, if that makes sense. So it's literally the same thing as a loop. For each blank, do blank. So let's build that function basically. So I'm going to make a function called square, which is a function version of the to the power of 2. So I'm going to say function of x brackets return x times x. So that's the same thing as x squared. Now I'm also going to create a vector. I'm just going to call this vector 1. And here I'll have a vector of 2, 4, 5, 7. So we've got our function called square. We've got our vector. Now let's say, very similar to your loop question, how do I apply square to each number in my vector? Here's where I can use map. I don't think I've loaded the tidyverse though, so I'm going to load the tidyverse right now, which brings per attached. We can verify that here once it loads. Yeah, we've got per attached. So I can say map vector1 square. So as I said a few seconds ago, for each vector1, do square. If I run this, it will then print out the square of each of those numbers. I can do the same thing with a function that I haven't created personally. I could just say vector1. Let's try cum sum, like that we were working with before. Okay, it's adding the cumulative total. Great. You know, any function you want. Something like mean though shouldn't work, because that would be taking the mean of the entire vector. Okay, so the reason this doesn't work is because it's taking the mean of 2, taking the mean of 4, taking the mean of 5, taking the mean of 7. That doesn't tell us much. If you take the mean of one number, it's itself. So that's less useful. So it's basically how map works. Map 2 takes 2 different values. I'm not going to go into what that looks like, but let me show you an example and walk you through how recently I've needed to use a per function called pwalk to do something in my own workflow as a data scientist. So in my job, I had a lot of surveys that I needed generated. So on Qualtrics, if you've ever used Qualtrics, it's like SurveyMonkey. You can download the survey as a JavaScript file. I had a lot of different JavaScript files that were modified slightly in R to be different things. And so I had a data frame with survey name, survey QSF, with the name of the file that I wanted it to be called, and then the file itself. So in this data frame, each value box under survey QSF was really long, had a lot of text there. And then what I wanted to do is take each of these and save it as a file name. Take this one, save it as a file name. So this should look familiar because I'm using pipes. I took my surveys tipple. I selected just those two, the name and the QSF. And then I did something called pwalk. So when you're doing a walk function in per, it basically says do something, but don't necessarily output anything. Do it and then you're done. Whereas map expects something to be returned. So I did pwalk, where I needed to declare what were my function inputs. So my function inputs were survey and survey name, which actually that should be survey QSF. I changed the names here before I wrote this in here. But we've got survey QSF there. And then what I want to do on those 2 inputs are write file, which is like write CSV, the name of the file, which is that value in the data frame. And then I wanted to save it to this subfolder where I wanted to take the survey name, which was this column, append the date to it, and then put .qsf because that's the file type. So you can see kind of the best reason to use these per functions nowadays is for when you're wanting to generate a lot of images in kind of a functional way. Instead of writing up 5 different versions of the same ggplot with different inputs, you might want to create a function that can run that ggplot and then give it different inputs and then have those all saved programmatically. That's a great use for per. If you want to save different files programmatically, that's a great use for per. If you want to run models across different versions of your data set, that's a great use for per. But besides that, most examples of how you can use per, most tutorials are just like things we already know how to do with across. And so it's very frustrating because there's new stuff. So there is a tutorial I've linked in my lesson that, when you need to learn more about per, just know that it exists basically. And when you have a certain issue, look on forums, look up how to figure it out, how to find someone else's code, or go through this tutorial. There's also a per cheat sheet that can be very useful. It's kind of finicky though. And as I said, most uses that we would be wanting to use it for are actually just to use across instead. So if you're ever wanting to do something across many different columns in your data frame, just go back to our lesson 6, where we talked about advanced data wrangling, and you'll be fine. So let me stop sharing my screen and stop recording.